It is clear that given a short bit sequence, or short bit stream, we can feed that through an interpreter and get a much more complex bit stream, something that has very rich behavior, that it's complex in some way, it's long. And so what we're going to do is discuss this in the context of something known as Kolmogorov complexity. So in compression, we have some kind of bit streams, like say this plant, and we'd like to feed it to a compression algorithm that gives us the smallest possible thing we can, and that we feed it back through a generic Java interpreter, spits back out our original bit stream. So the goal of compression in some sense is, given a target bit stream B, what is the shortest bit stream C sub B that outputs B? So it's clear that this is not optimal, right? We can take out some new lines, we can get rid of spaces next to this plus sign and so forth. So there's things we could do to shorten this Java program. Maybe there are other things we could do, like simplifying the logic. But I hope it's clear that there is a shortest Java program that outputs this plant, right? You can't have just a 1 byte Java program that outputs this. There is some shortest bit sequence that you put it through a Java interpreter and you get this. Okay? Now, more generically, we're interested in the question is, what is the shortest bit sequence period, C sub B? Not necessarily a Java program. And so my goal here is to convince you that this shortest bit stream for any language is closely related to the one just for Java. Okay? So let me make a very clear definition here. I'm going to say that given a bit stream B, the Java Kolmogorov complexity, K sub JB, is the length of the shortest Java program in bytes that generates B. So given some bit sequence, there's definitely some Java program, I don't know what it is necessarily, it's the optimal hug plant, for example, that will output hugplant.bmp. I don't know how many bits there are. So K sub J of B would be the length of this program in Java. And there definitely is an answer, but it just might be incredibly difficult to find. So what I want to do now is raise an interesting point. The Kolmogorov complexity, this thing right here, I called it the Java Kolmogorov complexity, but the Kolmogorov complexity is effectively independent of language. That is, if I pick another language like Python or C, it's not going to actually be different, not by more than a constant factor. Okay? And what I'm trying to address here is, you might raise an objection, and you might say, for example, well, Java only has certain primitives, right? It only has certain ways of drawing, certain types of loopings, recursion, whatever. Maybe some other programming language would have extra features that could make the program substantially shorter, maybe like C or Python or JavaScript. And so what I want you to think about, and this is a very challenging problem, but why is it that it doesn't really matter what language we're using? And so think about that for a moment. I'll give a hint in a second. Okay, here's my hint. Suppose someone has written a short Python program, and you are butting your head against the wall. You have, say, a gigabyte of bits, and someone's written a Python program that can output that gigabyte of bits, and in your case, your Java program, you can't come up with anything better than just hard coding it and printing it out, right? So if you already have an existing Python program that works, how can you write a Java program that is able to be short if you have a short Python? So the answer is going to seem a little silly, and I think it's easiest to understand by example. So suppose Sarah's written a Python program using her clever thoughts, and that program's really short, and I'm jealous and I can't think of a similar thing in Java to represent, say, hugplant. Okay, so she's come up with some far better solution. Well, even if I can't figure out how I can do it in Java, I could just be lazy and say, well, I'm just going to write a Python interpreter in Java, and then use my interpreter to run Sarah's program. Or in terms of our compression model, I can imagine creating one big old file that contains Sarah's code, maybe encoded as a string, and then my Python interpreter. And if you've taken 61A, you know interpreters aren't magic, they're just programs. And so when I feed this whole thing to the Java interpreter, I get back hugplant. So as a specific example, say Sarah's hugplant in Python is only 11,000 bytes. Then I write a Python interpreter in Java, let's say that's 100,000 bytes. So then in total, if I package that all together, that's 111,000 bytes in Java. And the important point here is that the size of a Python interpreter is constant. It doesn't depend on the specific bit sequence. It's just, that's an interpreter. And so what we can say then is that no matter what kind of clever program someone writes in Python, well, I just add 100,000 to that because that's the size of my Python interpreter, and that gives me the corresponding Java program. So in terms of our notation here, we could say that the Kolmogorov complexity in Java of a given bit stream certainly could be no more. It's less than or equal to the Kolmogorov Python complexity bit stream plus the size of our Python interpreter, which is just some constant, and there you go. Now the reason it's less than or equal to is maybe this isn't the best way to go about it. Maybe I shouldn't actually include a giant Python interpreter. I could do like direct code translation or something. And maybe the Java program actually ends up being shorter for some cases. But certainly we can say that it's going to be less than or equal to. And you can do this the other way around as well. Given a very short Java program, you could write a Java interpreter in Python and so forth. And in fact, you can show that, well, for any Turing-complete language, the size of the compiler or interpreter that you need to go from one language to another is always going to be some constant. So all languages that are Turing-complete are equally expressive. Now, what's a Turing-complete language? Well, that's beyond the scope of our course, but suffice it to say that all the usual languages, Java, C, JavaScript, all those folks, yes, they're folks apparently, they are all interconvertible with a constant space program. Okay? So what that tells us is that the Kolmogorov complexity is effectively independent of language. It's not that Hugplant is expressible only in Java compactly, but it is also expressible in Python and C and JavaScript, all of those languages. Okay. Here's another interesting fact. So not only is the Kolmogorov complexity independent of language, it turns out to be actually impossible to write a program that calculates the Kolmogorov complexity of any bitstream. Okay. Now, what I'm saying here is a little stronger than, you might have some intuition that it seems extremely difficult to do this in reverse. Given a bitmap file, somehow write a program that optimally produces it. This is actually saying that not only can you not write the program that will reverse this process, you can't even figure out this value here, this number of bits. It turns out to be logically inconsistent. If you had such a program, it turns out there's a logical fallacy that arises. You can check out the proof here, but we're getting way too into the theory of computation. And because it's impossible to even compute the length of this file, it is naturally, of course, impossible to write this, to write any algorithm that can give you the optimally compressed file here, right? Because if you could do that, you could just ask for the length of it. Okay? So the Kolmogorov complexity is a nice hook into understanding complexity. There are some bit streams that are complex, some that are not complex. However, given a particular bit stream, there's no way to even know how to compute that complexity. For some small cases you can, like, for example, just the letter A. In Python it's just print the letter A. There's no shorter Python program than that. But once you get to larger files or larger bit streams, it is impossible to compute the Kolmogorov complexity. But nonetheless, it is a useful notion because it gives us a fundamental understanding of what makes one thing complex and other things not so complex.